The article I'm presenting is Boron Switch for Selectivity of Catalytic Dehydrogenation on Size-Selected Platinum Clusters on Aluminum Oxide. It was published in Journal of the American Chemical Society by researchers from UCLA. So the big picture of this article is to use boron as a switch or a lever for tuning the properties of platinum-7 cluster catalysts. So platinum clusters catalyze the dehydrogenation of alkanes and also alkenes. And an issue with this type of catalyst is coking, which is the deposition of carbon on the active sites, which deactivates the catalyst. So if you want to dehydrogenate an alkane to an alkene, you want to stop it there and not dehydrogenate the alkene further, because when you do that, then you produce alkynes, which result in coking. And so they found that nanoalloying platinum-7 with boron makes ethylene more likely to desorb than to be dehydrogenated, and hence eliminates coking. So they created their catalytic material using mass-selected ion soft landing of platinum-7 clusters on alumina support. Mass-selected ion soft landing basically means they vaporized their platinum with a laser. They used a mass selector to isolate just the cluster size that they wanted, and then they focused that into an ion beam which deposits the clusters on the support. They exposed the material to diborane gas to nanoalloy it with boron. So this is diborane gas. If it looks a little weird to you, that's because it has these, what's called a 3-center 2-electron bond, also called the banana bond, and it's electron deficient. So basically this is 2 electrons being shared between 3 atoms. I thought it was pretty cool. They used temperature programmed desorption, or TPD, to study their catalyst. So TPD basically means you treat your catalyst with some sort of gas, and then you heat it over a certain temperature range, and you use a mass spectrometer to isolate the signal of the gas that's desorbing from your surface. And so they used carbon monoxide to probe the active sites, and ethylene to study the catalytic properties. And I'll point out that they used isotopes of both of these. So they used carbon-13, carbon monoxide, and deuterated ethylene. The purpose of this is so that they isolate just the species they're interested in, and this eliminates any sort of background effect from, say, atmospheric carbon monoxide. So they used ion scattering spectroscopy, or ISS, to get at the surface composition of their catalyst. ISS basically involves shooting an ion beam at your sample and measuring the energy of the ions that bounce back. So in this case, they use helium ions. The helium ions hit the sample, bounce off, and are detected by this electrostatic analyzer. And this gives them kinetic energy information. And the kinetic energy loss of those ions after they hit the sample is directly a function of basically the mass of the atom. And then finally, they used X-ray photoelectron spectroscopy, or XPS. So this is basically an application of the photoelectric effect. By hitting a sample with these X-ray photons, you cause electrons to be ejected. When you measure the kinetic energy of the electrons, you can determine the binding energy with which they were originally bound to the atoms. And that tells you not only the chemical species, it can tell you stuff like oxidation state. So it's really useful. In this case, they use it to look for residual carbon, or coking, after catalysis. And I thought it was really cool that all this was done with one instrument, some sort of special purpose instrument for making and characterizing these catalysts. And I wish I could have found a photo of it. Sounds cool. So with ISS, they found that they got about 80% coverage of platinum with the boron after treating with diborane gas. They then used thermally programmed desorption with carbon monoxide, and found a decrease in binding sites and weaker binding of carbon monoxide with the borated platinum. So this is a TPD readout. So these two peaks on the right, this black one is the untreated platinum catalyst. This one is just heat treated. And then these red and blue ones are the borated platinum catalyst. And so you can see not only do you have a reduction in the signal coming off when you desorb carbon monoxide, meaning there was less adsorbed to begin with, you also have a shift to lower temperature desorption, which indicates that you have weaker binding. And they attribute this decrease in the binding sites not to thermal sintering, for reasons I'll go into in a minute, but rather to the structures of the borated platinum-7. So they did the same with the ethylene to look at the actual catalytic properties, and they found that ethylene bound less and bound more weakly to the boronated platinum. And they also found that there was a 5-fold reduction in the deuterium produced, which means essentially there's a 5-fold reduction in the dehydrogenation catalyzed by the catalyst. So on top you have deuterated ethylene, TPD. So this blue peak is just the untreated platinum. Green and black are different heat treatments. And then over here, kind of stacked up on top of each other, are the borated platinum at different temperatures. So you can see that you've lost all this higher temperature desorption. Most of the desorption of ethylene is happening down here at these lower temperatures. And they included, for reference, this dashed red line, which is just desorption from totally uncatalytic alumina. And you can see that basically the borated platinum almost sort of mimics desorption from untreated alumina. So it's really not hanging on to that ethylene much at all. And then, of course, you have a reduction in the amount of deuterium produced, which is the whole point of this study. So they also found that after repeated reactions or repeated TPD runs, the borated platinum maintained active sites better than untreated platinum. And they also found this was true at higher temperatures as well. So, okay, so this green peak is untreated. This sort of reddish brown one is untreated after several runs. Over here is treated with boron, and then you can see basically right on top of each other, you have these two lines. So there was essentially no change in the ethylene desorption after multiple runs with the borated compound. And then you also see that in terms of deuterium produced, you have this huge drop from first run to subsequent runs with the untreated, but with the boron treated, there's basically no difference. So it's maintaining that catalysis better, even though it's less active. And then the carbon monoxide TPD is essentially showing that that active site coverage that you have is more stable with temperature after repeated runs. And then finally, XPS showed essentially no coking on the boronated platinum. So what this leads to conclude is that ethylene will desorb rather than dehydrogenate on the boronated catalyst. So in addition to the experimental work, they also did some computational studies. They used plane wave density functional theory, or PWDFT calculations, to model the boronated platinum structures. And they found that 10 isomers make up the ensemble of catalytic structures. So something that they point out is that the global minimum makes up less of the total population than in untreated platinum, what this basically leads to is that you have more diversity of structures with the boronated compound. And probably most important to this study is that they found that the boronated platinum favors binding ethylene in a pi configuration rather than sigma. So this is what they're talking about. On untreated platinum catalysts, highly active, you would have basically di-sigma bonding of the ethylene to the platinum. So each of these bonds would be on a different platinum atom. Instead, with the boronated compound, they find that both of these, this is essentially pi bonding to the platinum, and that means you're not activating that carbon-hydrogen bond. They also found through molecular dynamic simulations that the boronated platinum-7 clusters have much higher functionality. That means they're less likely to remain in the active configuration. So, in conclusion, boronation of the platinum-7 catalyst reduces its activity. Platinum-7 clusters with boron are much more stable against coking and possibly sintering. And boration provides a switch with which you can tune the properties of catalysts for alkane dehydrogenation.